Okay. Back in my element again. Just seems weird having you all not here, okay? But this is the easiest way to give this lecture, and I'm already here, and so anyway. All right. And I just feel so much more at ease teaching in this room. I just wish all of you were here. Because look, I'm seeing, Anna may be walking in a little bit late with a pass from the, from the physical therapist, and Jason rolling in going, hi, Anyway, miss all of you. Okay, so what we're going to talk about today is what's known as the standard enthalpy of formation. I'm going to tell you right from the beginning, I'm going to show you the long way to do this, and then I'm going to show you the shortcut way to do this. The long way is more conceptual, but I will never expect you to do the long way on an assignment or a test, okay? But it's important that you understand the long way around this thing. So let's start with what the definition of standard enthalpy of formation is. So standard enthalpy of formation is basically, let's say that you want to form any substance other than the elemental form. So like if you want to make oxygen, that's just an elemental form. There is no standard enthalpy of formation for oxygen or nitrogen or hydrogen, any of the elements. They're not there. So what you're going to do is you're going to end up looking in the back of your book. I think it's page 1088. And you're going to have this, and this is going to become your friend. There's this whole chart that gives all of these different values. Enthalpy of formation, which is this delta HF. Standard, then you have your entropy and your enthalpy, okay? So those three things are going to be very important. You might put like a tab on that page because you're going to be using that so often as we go through this. So the definition of standard enthalpy of formation is basically the energy associated with making an element or making a compound from its elemental form. So for example, let's say that you want to talk about making aluminum chloride. Well, there's 100 different ways that you can make aluminum chloride. You could take, a single displacement reaction between aluminum nitrate and sodium chloride. Oh, that would make you aluminum chloride. There's any number of different ways. But so that we're always going off the same idea, you're always making it from the elemental forms. So let's say that this is like the Chem 1 way this is written. Here's the normal balanced equation. 2 aluminums plus 3 HCl2 use AlCl3. So the golden rule about this is that you always want the coefficient to be 1 in front of the compound that you're going to write. So you write and balance it normally, and then you basically divide everything by whatever that coefficient is. So because of the fact that we want this coefficient here to be 1, that's why we divide everything by 2. So when you write that equation, it's Al plus 3 half Cl2 plus AlCl3. And don't sit there and go, Mr. Burkamp, we can't have 1.5 chlorine molecules. You're right. You can't. But from a standard enthalpy of formation, the way this is written, you always want that coefficient to be 1 in terms of that final product. Now, if you go and look up in the back of the book, you'll find that the enthalpy of formation for aluminum chloride is negative 705.6. So what that means is that this is a very exothermic reaction. So if you take aluminum and you react it with elemental chlorine, you are going to get a lot of energy released from this process. If you notice, almost all of them, no, not all of them, almost all of your enthalpies of formation are negative values. So generally what that means is that the products, the aluminum chloride in this case, have less energy than the individual reactants, the aluminum and chlorine, okay, because it's an exothermic reaction. Sometimes you have positive values. For the most part, they're almost always negative. So here's what we're going to do. And again, this is going to be this long process. I don't ever expect you to be able to do this, but it's important that you understand the concept. So we're going to look at a reaction between ammonia, NH3, oxygen gas. We're going to produce nitrogen dioxide and liquid water. And again, this is going to be important. We're going to produce liquid water because there's two sets of thermodynamic data for water. One is a vapor, one is a liquid. You have to pay attention to what form this is in. So here's what I've got. So you've got ammonia, NH3, so happen to have ammonia. And you're going to have oxygen like this, okay? So these are what you're going to start with. You have ammonia, you have oxygen. What we're going to end up producing is water and nitrogen dioxide. Okay, so these are what we end up with. So you're going to start with this, and you can end up here. Okay? Now, what I'm showing you is this. To make this happen, you've got to take that NH3, which is this, and what you're going to do is you're going to conceptually break it up into two different things. You're going to break it up into 6 hydrogen molecules, okay, like so, and 2 nitrogen molecules. So I know that because I want this number of particles to stay the same. So I've got 12 hydrogen atoms. So this is why this adds up to 12. And then I've got 6 here, and I've got the 4 nitrogens, and that's why that's 2 in 2 here. Now I don't do anything with the oxygens because I don't have to break them up into their elemental forms. This process is just showing what's happening when you break it up into the elemental forms. Now, what we're going to do is we're going to combine some of these. So we're going to take like all of these nitrogen molecules and some of these oxygen molecules, and we're going to produce 4NO2. Then we're going to take all of the hydrogens with some more of the oxygens, and we're going to produce liquid water. Okay? Now, this is the long process. Don't flip out and go, oh my God, Berkemp, are we going to have to do this? No, you won't. Okay? You won't. Chill out. So, again, this is the long process. So, what we're going to do is we're going to look at the idea that we're going to take ammonia and we're going to break it up into this elemental form of nitrogen and hydrogen. I went through and I divided everything to get a coefficient of 1. Now, when you look at the back of the book, the standard enthalpy of formation for ammonia is negative 46.19. Okay, that's on the formation side. But because we're breaking it apart, we're going to switch this sign and we're going to make it positive 46.19. Now, that's got to happen 4 times. So we're going to take 4 times 46.19, and I just rounded this to 184 to make the math work out. Now, on your NO2, you're going to go through and you're going to look up the thermodynamic value for NO2, which in this case is 33.84. So what that means is if you produce NO2 from the elemental form of nitrogen and oxygen, this is actually an endothermic reaction in this direction because it's a positive value. I didn't switch this sign. If you look at your back, if you look at the table, this is actually already a positive value. So this isn't positive because I reversed it. This is just straight up positive in that enthalpy of formation. Now for water. Water, I've got negative 285.83. So, and again, this is as it is written, okay? This is 6 times negative 285.13. So, and again, do not flip out. I'm not going to expect you to know this, but this is the important part in terms of the conceptual side of this. So, your one option is that you take the compounds, you break apart any of the reactants, you reform the products, and you go through and you do all of this and you write out all of these equations. But that's fundamentally what's happening in terms of the reaction, is that you do separate them into their individual molecules. You recombine them into something new. So, if you add all this together, you get negative 1396. So what that means is that this overall reaction is very exothermic. You're going to get a lot of energy released from this. So if you can take ammonia, basically react it with oxygen, and to produce NO2 and liquid water, you are going to get a lot of energy out of that reaction because you have a huge negative delta H. Okay, now that's the long way to do this. Don't flip, I'm just telling you, that's the long way. But now that you understand this, then the shortcut makes a little bit more sense. So this is what's on your equation sheet, okay? And here's the shortcut, and here's what you're going to see, whether this is entropy, enthalpy, doesn't make any difference, or Gibbs free energy, they all have the same form, okay? They all have the same form. So in this situation, it's always going to be products minus reactants, okay? I cannot emphasize this. It's always the sum of the products minus the sum of the reactants, okay? It's always the same thing. Just like in calculations of like KSP is always products over reactants, this is products minus reactants. So here's what you're going to do. Your products, and you have to reverse this, your 4 products are NO2 and 6 water molecules. Your reactants are NH3. Now, you do have a reactant of oxygen, but there is no enthalpy of formation for oxygen. So there's oxygen there, but we don't have to worry about it because that's just going to be 0. So when you look at this, okay, so you're going to come in here and you're going to take the 4 in your NO2s, and I just rounded this to 34. Okay, you actually want to use the whole deal, but I just use this to save some space. So you're going to find the NO2. You're going to look up water. Now, here's the odd thing with water. Water is, if I remember right, in your book is actually under the oxygen section. It's listed by elements. You would think water might be under like the hydrogen section. It's not. It's under the oxygen section. So that's a little bit weird, but that's what it is. So, and then you've got the 4 NH3s. So when you do this, you don't have to worry about switching the signs, okay? You use these numbers straight up as they are. Do not switch the signs of anything. This is the beauty of subtracting this thing. So the subtraction will take care of any positive or negative signs. So you have the sum, so you're going to look up the 4 NO2s. You're going to go to the back of the book. You're going to find that index, and you're going to find, and make sure that you're keeping track of your enthalpy of formation, your delta H column. You're going to have 3 columns back there. Delta H, delta G, and delta S. Okay, make sure that you are paying attention to the delta H column. So, you're just going to add these together. So you can take 4 times 34, plus 6 times negative 286, minus 4 times negative 486, and notice that you get the exact same answer. So, here's the beauty of this as well. What you can do is if, and this is how this plays out in the lab setting. If you know what, for example, what the overall reaction is, that negative 1396, maybe you don't know what the enthalpy of formation of NO2 is, but you can measure the enthalpy change for the entire reaction. If that's the case, then maybe you come in and you solve for this. Okay, we've known water for quite a while. Maybe we know the NH3, that's a pretty common compound. So if we can do this reaction to figure out the overall reaction, that would allow us to solve for a particular unknown variable. So once you don't have to run every possible reaction to find out every possible thing in terms of the enthalpy of formation. So you can actually solve for a variable if you know what the overall reaction is. Okay, kids, there's that, and I will send out the answer key to this, and there we go. All right. See you, kids. Bye.